behalf of the whole SDSS team, I would like to thank Sigmund for the Systems Award. We are an amazing company. This talk is about a 30-year journey into database-centric scientific computing. The Sloan Digital Sky Survey started in 1992 and finished its original plan in 2008. It took twice as long as originally planned, but it enabled us to be much more ambitious in terms of the data processing and data analysis end. And we planned to take 2.5 trillion pixels of images. We ended up with 6.5 trillion pixels of the sky, and our database grew from the planned 0.5 terabyte size to 35 terabytes in the end. The project is sometimes also called the Cosmic Genome Project. It is the astronomy equivalent of the Human Genome Project. We had the privilege to work with Jim Gray, and it is interesting to spend a minute on why did Jim find astronomy interesting. And generally, astronomy has always been data-driven for thousands of years, because astronomers cannot go to the lab, push a button or turn a dial, and then something happens to a star on the sky. All that we can do is passively observe what is happening on the sky, and then based upon what we observe, come up with new experiments, new ways of observing the systems, and figure out the physics of it. So when Jim was spending half of the time working with us, he was interviewed by Bill Gates doing his annual review. And Bill asked him, why are you spending half your time working with the astronomers? And Jim's response was, I love working with them because their data is worthless, meaning the data has no commercial value. And the important thing about it is that when we were working together, we didn't have to bring in the Microsoft and Hopkins lawyers, we didn't need NDAs, and we were just able to share the data freely because there was really no commercial value. And we had a copy of the database running inside Microsoft. Our first data release was in June 6, 2001, when the telescope was operating only for 2 days. This is almost exactly to the day 20 years ago. And this yielded about 100 gigabytes of data, a few hundred square degrees of the sky. We got the data about 2 weeks before the official data release, and Jim and I worked 20-hour days during those 2 weeks, but we actually got the database built. The first real data release came then in May 2003, which was really well calibrated, the first terabyte of catalog data, linked to about 6 terabytes of raw data loaded by Anita Carr. And then the whole website that we built got also a major facelift from Curtis Wong, who later built the Worldwide Telescope. This was followed by the regular, typically annual data releases, and now we are on data release 16. But every data release version has been kept alive, like the editions of the book. We don't burn the previous editions, we still keep them on the shelf if someone wants to read them. Astronomers like to use spatial relations to analyze the structure of the universe, so spatial tools are everywhere. And we had almost 1 billion object outlines, tens of thousands of geometric boundaries, and millions of masks representing saturated pixels, and a very large dynamic range of scales. And we had to perform fast spatial searches. At the time, there were no libraries available, so we had to write our own. And we wrote our first version inside SQL Server using computational geometric tools programmed in SQL, and only Jim could do this. And later on, we converted it to C#, and this was actually the first demo of the CLR framework for SQL Server in 2005. We were in the Schindler box. We also built additional extensions, in particular the server-side analysis tools. So we gave users their own SQL MyDB, so a little SQL Server database which was able to do joins with the main read-only database, and the users could do anything in their database, and even essentially doing cloud computing in 2003. They could form groups and they could share tables and collaborate. We also were logging every mouse click since the day one when we released the data, both on the web interface and in what happened inside SQL Server. This is now several terabytes of data, which was widely shared within the CS community for workflow analysis. We built the Sky server, which formed the main portal into the data, a highly visual interface. And we had over 3.6 billion web hits in 20 years. People typed in 620 million external SQL queries. It resulted in 10,000 refereed papers and 500,000 citations. We had 9 million distinct IP addresses using the data versus 15,000 astronomers. So it was clear that something else is happening. And we saw the emergence of the internet scientists who made original discoveries using the nicely calibrated public data. And up to today, this is still the world's most used astronomy facility. And the collaborative kind of cloud framework is the server-side analysis tools are used by more than 10,000 astronomers. We gradually evolved the Sky server to Sci server. So realizing that everybody, not just astronomers, wanted service-oriented smart data. They wanted to collaborate, they wanted to do interactive science, and they also wanted a secure core for the main data sets, but they wanted to do free-for-all, very creative analysis in their own space. And what we saw is that increasingly complex analysis patterns emerged. And we found that also these tools started to be used by other disciplines, including genomics and turbulence and fluid dynamics, ocean circulation. But we also saw science of service lifecycle after 15 years. After all, the original version was kind of put together in a very short time. And the NSF gave us a large grant in the DIPS program to do a comprehensive overhaul under the hood and basically isolate the astronomy components and create a CRISPR API under the hood that can be reused in other domains. And this shows, the figure here shows basically how many different disciplines and projects are today on the Sci server, including IPython and R scripting. And we even have various cloud versions, both in Azure and AWS. So the broad impact of Sloan is very significant. It really changed the way we do astronomy. And what we saw is that the astronomy community has been amazingly fast in adapting to these new tools and learning how to use a database. And today, astronomers use the database tools not as a hammer, but as a violin, and they really play beautiful music with it. Sloan earned the trust of the community by providing basically over several decades a consistent, stable platform, which is providing very clean and reliable data. We saw an enormous number of projects way beyond the original vision. People did some amazing new discoveries in the data that nobody foresaw. And now it serves as a model for other communities of science. Moreover, it demonstrated that database can be powerful tools for science and help to create citizen science in the Galaxy Zoo project, creating major new discoveries by internet scientists. And we also see the genealogy of the Sky server. So basically it started with Jim's Terra server that was built at Bark, and then we built the CastJobs and MyDB, and it had many, many spin-offs, and the latest is the Sci server. In summary, what we see is database-centric computing is everywhere in science. Data-intensive science is a very hands-on field, and most of the progress is made through trial and error, so we need to have an interactive and collaborative framework. Everything is spatial, requires indexing, and this means actually databases are a perfect foundation, but we have to build a lot of extensions, incorporating various domain-specific knowledge to business intelligence of science. The declarative approach to programming works very well with big data when we don't really have to, the users don't really have to understand how to build the iterators over a distributed framework. We saw that the CastJobs, the innovative collaborative features are basically very well received by the science community. And in the Sci server, we see now that our data sets are used, for example, creating new data sets for machine learning and deep learning. We see right in front of our eyes, Jim visions come true. The fourth paradigm of science is emerging. And we are proud to say that Sloan, the SDSS project, has been at the cusp of this transition. And we had over this project several generations of people who worked on enhancing the data. And they are all on our team. And I would like to list them all by names. And we are extremely happy to see that, you know, Jim is also on the list. And in the meantime, Jan Vandenberg, who was our main systems administrator and systems designer, he was still aware of the ACM prize, but he passed away about a week after the announcement of the ACM Sigmod Award. So I would like to thank one more time ACM Sigmod for this recognition, not just on behalf of the SDSS project, but on behalf of the whole science community. Thank you very much.